All right. So last time we talked about covalent bonding. Essentially, what we see is that through electronegativity, that certain elements want to take electrons more than other elements. And again, we're going to be talking about more about covalent bonding, more about the Lewis-Dach structure and how that's going to tell us how covalent bond is going to occur. Okay, so just a few vocab words before we get going. Again, with nonpolar covalent bonds, we see that because the difference in electronegativity between two different elements is very low, uh, the bonding is going to be very equal distribution of electrons. With polar covalent bonds, what we see is that there's going to be unequal distribution for the electrons that we see here. So again, water is a good example of that because the oxygen has more electronegativity than the hydrogen. So because of that, there's going to be a slight change in the distribution for the electrons in that bond. So again, the oxygen would be more negative while the hydrogens would be more positive. Okay, so moving on to the covalent vocabulary, we got to talk about single covalent bonds and unshared pair, so lone pairs that you may also call them. So, with single covalent bonds, what this is showing is that there is one pair of electrons being shared between two elements. So, if we look here, that these two chlorine atoms are sharing one pair of electrons. So, again, the chlorine, their electron, this chlorine's electron are being shared. And how we show that there is a covalent bond is through this single line here. Again, this is showing us that because of the sharing, that both the octets, both shells for the chlorine atoms are filled in. An unshared pair is a pair of electrons that is not being shared. So again, if there isn't this line here showing the covalent bond, all of these electron pairs here are going to be those lone pairs. And again, they'll have their own charge based on, again, the charge that is being seen. But again, this pair here is a lone pair, this pair here is a lone pair, this pair here is a lone pair, lone pair, lone pair, lone pair. So again, it's those pairs that aren't seen or aren't being used for some type of covalent bond. A double covalent bond is the sharing of two pairs of electrons between atoms. We see this with oxygen. So again, two pairs of electrons are being shared between the two atoms. And then a triple covalent bond is going to be the sharing of three pairs. So again, what we see is that with the two nitrogen atoms covalently bonding, they form a triple bond. And you have a single lone pair here and a single lone pair there. So again, the triple covalent bond, double covalent bond, essentially what it's saying is just how many pairs of electrons are being shared between the two atoms. So looking at the Lewis-Dach structure, this is going to represent the molecules showing electrons bonding and non-bonding. So again, we see with the hydrogen bonding with the hydrogen, so H2, what we see is that there are no lone pairs, but there's that single covalent bond. But with chlorine, what we see is that there's a single bond, but there are three lone pairs per chlorine atom that we see. To help you understand how many bonds an element usually forms, you draw its dot structure and count the number of unpaired electrons. So for this example, we look at oxygen. There are two lone pairs. There are also two unpaired electrons, so that is going to tell us that there are going to be two bonds to form with that oxygen. With the chlorine, we see that there are three lone pairs, and there is just one single unpaired electron. So again, you'd see one here. We look at phosphorus, we see one lone pair, but then we have three unpaired electrons. So again, that'll form three bonds, covalent bonds. And then with carbon, we have four unpaired electrons, so it's going to form four bonds. Writing the Lewis-Dot structures for different molecules, we got to find the sum of valence electrons of all atoms in the polyatomic ion or molecule. So if it is an anion, you're going to add one electron for each negative charge. If it is a cation, subtract one electron for each positive charge. So if we look at phosphorus and chlorine here, we see that both of them have a neutral charge. The phosphorus has 5 valent electrons, so we're going to do 5 here. And chlorine has 7, but we have 3 chlorine atoms based on that subscript that we see. So again, 3 times 7, that's 21. 5 plus 21, that'd be 26. So there are 26 available electrons seen here, or valence electrons. What we see when we write out or show this compound, we see with this molecular polyatomic, is that the central atom is going to have the least electronegative element. So that is going to be seen in the middle, okay? Except for hydrogen. Again, hydrogen is its own rule in itself. But what we see is that with the least electronegative, again, it's going to be the central atom. It's also the atom you have the least amount of. So what you're going to do is you're going to connect the outer atoms to it by single bonds. So again, we got to keep track of the electrons, what we see here. So I know that with phosphorus, it's going to, again, be used with the 3 unpaired electrons for each chlorine. So again, we take away 6 with the bond here. So in this example to the left, 6 electrons are used because there are 2 electrons per bond drawn. So again, there's 3 bonds being drawn. So again, 6 electrons being used. So there should be 20 valence electrons available after the bond that we see here. After we do the bonding, then we fill the octets of the outer atoms. So again, we draw the 6 for each one here. And then we have 2 electrons left after drawing all the paired electrons for the chlorine, for all the chlorine atoms that we see. And again, we finish up by adding the 1 lone pair that we see with phosphorus. So again, all of our valence electrons are accounted for. But what we see is that if they do not, move to Rule 5, and Rule 5 will be seen on your sheet. And again, I'll show you that in a quick second. But what we see is that, again, we have our 6 valence electrons being shown between the chlorine and phosphorus atoms. We have our lone pairs for the 3 chlorine atoms and the phosphorus atom, and then that should add up to 26. Again, we used up all, and we kept track of the valence electrons that we saw. Rule 5, if you have too many electrons in your structure, you're going to need to form multiple bonds until it has the right amount of electrons. So again, what we see here is that with carbon, there should be 4 valence electrons. Hydrogen, there should be 1. Nitrogen, there should be 5. So again, we're looking at 10 in total. So we have 2, 4, 6, 8, 10, 12, 14. So again, we'll do a triple bond here. So we got 2, 4, 6, 8, 10 to show that the valence electrons are good and that everybody is happy. All right, that'll do it for writing Lewis dot structures. Again, look back at this video if you have any questions or concerns with this.